Okay, so we're going to work a calculation to determine what the concentration of free metal ion is in a solution where a complex is being formed. And we're going to base this on our copper ammonia complex that we observed in our demonstration just a little bit ago. So we're going to set up a situation where we prepare a tetra-ammonium copper complex in a solution where the concentration of Cu2 plus is 0.20 molar and the concentration of NH3 is 6.00 molar. So that's our setup, and what we're going to calculate is what is the concentration of free available copper once this reaches equilibrium. It's not 0.2 molar. It's much less, because once it forms a complex, it's no longer free copper 2 plus. It's not 2 plus anymore. It's copper tetraammonia complex. Okay. So we need an equation for this reaction. Cu2 plus 4 NH3s are both aqueous in equilibrium with CuNH3 by 4. Everything is aqueous, so we really don't need to show any of the states, but we can. And we set up an ice table. So in our ice table, we put in our initial conditions. Our initial conditions involved 0.2 molar copper and 6 molar, a large excess, of NH3, and no complex formed yet. Then as we allow this to change and reach equilibrium, we have to worry about the change row. So of what we have right here, hopefully we can all agree that the 0.2 molar copper runs out first. Ammonia is used 4 times as fast, but there's more than 4 times the amount of ammonia that there is copper. So we're going to lose 0.2 molar copper, and we're going to lose 4 times that amount, or 0.80 molar ammonia, to make 0.2 molar copper ammonia complex. We lose 0.2 amount of the copper 2 plus because it's all going to get consumed. It's our limiting reagent. Then we lose the stoichiometric equivalency, 4 times that, of ammonia to make the stoichiometric equivalent amount of copper ammonia complex. So this is one of those with a large K value. I had it up on the screen last time when we worked the example. Kf for the copper ammonia complex is 5.0 times 10 to the 13th. That means that this is an ice table because we have a large K, we've let everything go to the right, now we're going to see how much trickles back. Because at the intermediate stage, now we have no copper 2 plus. For ammonia, we have 5.20 molar, because we lost 0.8 molar out of our 6 molar, and we have 0.20 molar copper ammonia complex. Now we let it reach equilibrium from here. It's like starting over. This is our new initial set of conditions. We go through a change again. We're going to lose X amount of copper ammonia complex, which means we gain 4x because of the 4 coefficient amount of ammonia, and plus X amount of free copper ion. That's really what we're after. So now at equilibrium, we have 0.20 minus X, 5.20 plus X, and X. Now again, just like we've done in the past, when we get to the end of our ice table at equilibrium, we look at all of the molarities that have a number and a variable. And we want to see if we can drop the X's on those terms. So we compare those concentrations to Kf. And there's more than 100-fold difference between those concentrations and Kf, which means we can drop those X values because they're negligible compared to the number they're associated with. Then we set this all up into a KSP problem in the past. Now it's KF. So KF for this situation, products over reactants, equals the concentration of CuNH3 by 4 over the concentration of Cu2 plus times the concentration of NH3 to the fourth power. Don't forget the fourth power there. And that is a numeric value of 5.0 times 10 to the 13th. So now we have either numbers or variables to plug in for everything on the left-hand side now. So we're solving for Cu2 plus. This time I'm going to solve for Cu2 plus out of the equation before I plug in the numbers. So Cu2 plus is going to move into the numerator. The K value is going to move into the denominator because of where they are right now and where they're going. So the concentration of Cu2 plus equals concentration of CuNH3 by 4 over concentration of NH3 to the fourth power times Kf, which was 5.0 times 10 to the 13th. So now we can plug in the numbers out of our ICE table. So our ICE table said that the concentration of CuNH3 by 4 was 0.2 molar. Divided by NH3 was 5.2 molar. That gets raised to the fourth power times now Kf, which is 5.0 times 10 to the 13th. So the concentration of Cu2 plus, we're ready to calculate that. So 0.2 divided by 5.2 raised to the fourth power. And on my screen right now I have 2.74 times 10 to the minus fourth divided by 5 times 10 to the 13th. So I get 5.47 times 10 to the minus 18th. That's the available concentration of Cu2 plus that has not formed a complex. Very, very tiny concentrations, one of the smallest concentrations we've seen thus far in the class. So what that represents there is only about 10,000 copper ions per liter of solution. Very, very low concentrations. Now all the KF problems are going to work like this. You'll need to know the concentration of the metal ion, the concentration of the ligand. You'll need to know the KF for the complex. Then you set up an ICE table. All the KFs are large, so they're all vanilla ICE tables. Find out what your intermediate stage looks like. Usually it's the metal ion that runs out first. So find out what your intermediate stage looks like, see what your variables look like after that, and come up with your equilibrium concentrations. Since all of these KFs are large when we work them, they're all situations where you can drop these X's. Once you know what your variables are, set up your KF expression. KF expression is the complex divided by the metal ion divided by the ligand, all raised to their appropriate powers. Then plug in what you know and come up with the metal ion concentration at the end. Okay? Good luck.